John here. Let's talk now about the so-called min terms and max terms. All right, max terms are expressed, as you will see, with an uppercase M, and they're numbered like this: M0, M1, M2. The min terms are lowercase m, and they're numbered M0, M1, M2, and so on. All right, now bear with me. There's some notation here. Then this hopefully becomes somewhat intuitive when we take a step back and really think about what's going on here. So bear with me here. This is going to make our lives a little bit easier as we move forward into higher level concepts. So the min terms are also referred to as SOP, which we refer to, this is an acronym standing for sum of products, which I non-intuitively define way down here. Maybe I should update this handout. Nonetheless, we're good, okay? All right, so what is sum of products? Okay, well, the summing and the producting, this goes back to the top of the handout. Well, some people like to think of the AND function and express it like we use this raised dot or just expose variable names together like this, a lot like, and it doesn't in cases behave like multiplication. So quite often you'll hear people refer to the AND operation, the Boolean logic AND, as a product. And it sort of is. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is in fact 1. So in a way, this is kind of multiplying. All right? Now what about the sums? Well, if you understand or accept that there's a thing called saturated arithmetic, a saturated accumulation, right? 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. All right? Now, the idea of saturation comes in when you say, well, what's 1 plus 1? Well, you want to call it 2. Well, saturated addition means there's nowhere to hold all the, that information. So I'm going to throw it away, but I'm going to saturate the value. I'm not going to add 1 and 1 together and get 2, which in binary is a 1 followed by a 0. This right here is the value 2 in a 2-bit number, right? You may be familiar with the fact that, you have overflow, and we'll talk a lot about overflow later on in this series. Where the 1 here is thrown away, and then the sum is 0 with a carry. Well, in saturated arithmetic, what you're doing is you're saying, I've already run it up to the maximum, so I'm going to leave it at the maximum. All right? This is saturated addition here. All right? And that's, again, why some people put the plus in here. All right? But you got to be careful. Always maintain what context you're dealing with. Are you dealing with saturated math, or are you dealing with, addition of decimal numbers, addition of binary numbers? Keep the context right. All right. Anyway, so the point here is that when you speak of sum of products and product of sums down here, in the concept of applying the mathematical operators rather than the logic ones, that's where these words come from, okay? Just so you kind of see what's going on. We'll just, for now, continue to consider that as an interesting side note, okay? All right, what is a min term? Well, let's fill it up with more stuff to memorize, followed by a step back and say, we don't actually need to memorize this because we can recreate it once you understand what it all means. All right. Okay, so some formalisms here. In a min term, each variable may appear only once as either itself or with a bar on the top of it. All right. For a 3-input function, we already know there would be 2 to the 3rd power number of rows in a truth table that expresses all the combinations. 2 to the 3rd is 8. And in this case, we have 2 to the 3rd min terms. As you're going to see, these min terms represent a row in a truth table. So there's a lot of terminology and formalism. I'm not a real big fan of that. Let's just bear with this, okay? What is this doing? We're giving a name to the row in the truth table where this expression here is true. When A bar is true, that means A is a 0 for that to be true. And when B bar is true, well, that means B has to be 0 for this one to be true. And C bar is true. Well, that means all A, B, and C have to be 0 in order for M0 here to be true. And that occurs once and only once in any truth table that enumerates all of the input combinations, or each one of them appears only one time, as I explained before, is the right way to express a truth table. So M0, we can say, is true when A is 0, B is 0, and C is 0. Okay? Look at the next one. M1 is true when A is 0, and B is 0, and C is a 1. Well, M1 is only true for this row here. 001 does not appear anywhere else in the truth table, therefore M1 is true only for this row, okay? So what we're really doing is abstracting away all of what's going on in here, which only serves to confuse me, to be honest with you. But let's accept this terminology. We can speak in terms of these little m numbers now. Let's say I want to express a function. It's described like this over here. And I want to just say, hey, here's a truth table. Here's the inputs. Ignore everything on here except for the A, B, and C inputs here. And the output column I'm going to call F over here. All right? If I give you a truth table and says, here's your inputs. Oops, too much highlighting. If I give you these inputs here, and I give you this output there, you can say, look, F is true when M1 is true, which is this case here, or when M2 is true, which is this case here, or when M4 is true, which is this case here, or when M7 is true, which is this case down here. Okay? Again, tracking back through all this stuff here. Look at these bars, and look when they appear and when they don't appear. What do we see in here? We got bar, 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 no bar, bar, no bar, bar. These bars, if you look, kind of gaze your eyes at that table up there, and then you gaze your eyes at this thing down here, if and only if you count in order, in binary, from 0 up to the maximum value, the bars that appear up here describe the inputs when this is true based on when there are zeros over here. Look at that. A bar, B bar, and C bar are all zeros. The bar, 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 that's M0. M1, we got bar, bar, and then no bar. Well, that's bar, bar, and no bar. No bar is when it's a 1. All right, and you think about this for a second. Of course, duh, right? Well, when is M7 true? Well, that's when A is a 1, and B is a 1, and C is a 1. Well, that's down here, and then you can see clearly that they're all 1s. And if I want my F to be true in only these cases for M1, M2, M4, and M7, well, it makes sense that if I were to express this M7 over here, you can clearly see it appearing down here as I expand these abstracted away details here. M7 represents this expression here, which I explained right here, right? Equation 55, right? So what we're really doing here is I'm saying, look, if I want to say, I want to define a function such that its output F is true in these cases, what I really can't, one way of doing it is just identifying each of the rows in this table when the output is a 1. And that's exactly what this is doing. If M1 is true, or M2, or M4, or M7, these 4 cases I want F to be a 1, and all other cases I want it to be a 0. Well, logically, I can take each of these functions. Now let's look at the details here, right? A bar, B bar, C bar. When all these 3 inputs are true, only occurs here, that's a 1. In all other cases in this column, you can see that they're all 0. In this case over here, which represents M2, okay, here's your M2 case, 010, you see bar, no bar, bar, right? The bars coincide with these zeros in the table. Then, and only then, does this guy represent a 1, the case when there's a 1 in here. All the other cases are 0. This guy over here is the definition of M4. Okay? Clearly you can see M4, 1 double 0, and you see no bar followed by a double bar on these guys. That describes this one case here. All other cases are 0. And the M7 is true if and only if all of the inputs are 1s. And you can even see that's the AND operation, right? It's a 3-input AND operation, A and B and C. Only when all 3 are true do we have a 1 here. All other cases are 0. We can then simply OR those together. In this case, or that one, or that one, or that one. That's when I have this output to be true. I don't have to worry about what it means. I don't have to worry about, could that be the implication? Who cares? I want this to be true in these 4 cases. I don't care why. I just want it. Make it so, right? If you watch Star Trek, that's Picard. Make it so, is always what he used to say, right? So, all right, a related note, big picture thing here. I will make an observation. By the way, this column here describes a 3-input exclusive OR. Look what's going on here. Remember, XOR is true when there's an odd number of inputs set to a 1. Well, there's an even number of inputs. 0 is an even number, therefore it's false. Here's an odd number of 1s. It's true. Here's an odd number of 1s. True. Even number of 1s. False. Odd number. True. Even. 1 and 1, right? 2. There's 2 here. Those 2 cases are false. And here's another one where there's an odd number of inputs that are set to 1. This is a 3-input XOR, okay? Now, yes, if you would have noticed that on at the beginning, we could have just said, oh, yeah, F equals, A XOR B XOR C. Done. However, we don't have to worry about that. We can just write it out longhand. Yeah, this is bigger, uglier, and messier, but you don't have to think. You can always do this. It always works every time, all the time, guaranteed. I can always define any function using the sum of products, okay? And it's proven and discussed in great detail up here in this footnote number 3, which is, I don't know, down here somewhere. Here's a book over here. It's a little dry reading. There's a link in here to the actual page. I just checked it out. This is like a Google book or something, and they can show you the 1 or 2 pages. You can read all about it if you want to know. Just the takeaway here is that you can always express a Boolean function in SOP form. All right? And you use this technique right here. All right. Now, oops. Yeah, that's correct. I'm scrolling around. I can't see what's going on. All right. Sorry about that. Again, I note that the presence of the not bars coincide where you see the zeros. I talked about all that stuff, right? All right, so here's how you can express all this stuff. Personally, I rarely use this notation up here. Yeah, it's easier to write, but I can't see what's going on. If I do sum of products and products of sums, I always write it out longhand like this, all right? That's just the way I do it. If I give you a homework assignment based on these, you do need to know how to translate them back and forth. I'm not saying ignore this. I'm saying on your own, on my own, I usually work in the more verbose mode here. Okay, so as we look at this truth table again. Top I. What are the mechanics of doing this? Okay. The mechanics of driving this equation. How do you determine how to do this, right? You draw up this truth table and you identify those specific input patterns where the input will, or the output rather, will be true. Just like I said, when F is 1 over here, then and only then do I want to identify these cases and grab an expression that is true, then and only then for that one row in this table. And you can clearly see there's a 1 here and a 1 there and a 1 here and a 1 there. What are the other observations? Well, if there's 4 terms here, there's going to be 4 cases when there's a 1 in the output, okay? And by ORing all these things together, each one of these 4 cases represents the 1 over here, and all other cases it will be false. Okay? So little intuition. You should always be able to check your work. I got 4 terms. I better have 4 1s over here. Okay? When I'm in sum of products. Okay? Product of sums works the other way around. And you can start to smell the Morgans Theorem coming in here. And we'll talk about that in a minute. Okay? So how does this thing work? In max terms, you flip it around the other way. Instead of using the AND function like we did above, we're going to use the OR function. All right, let's review really quick. The max, or rather, this is the min terms. The lowercase m is min terms. We have all of these expressions. Each of these expressions shows each and every one of the inputs, either with or without the bar. And they are only allowed to occur one time in this expression. Every single one of these rows, all inputs, all three of them, every time, with or without the bar. And in every case, they're all ANDed together. Okay? That's sum of products, min terms. Down here, we see the exact opposite. This is going to be product of sums. Remember, the sum is like the OR, saturated sum, right? Again, each of the three inputs appears once and only once, either with or without the bar. And they're all ORed together in this case. All right, so let's look at the introduction note up here. Same as the min term, like I just said. However, we're using OR instead of the AND. Okay, almost the same. Okay, note, subject to this note, the not bars. Okay, again, look at what's going on. Like when you count in binary, you got 000, 001, 010, 011 in binary. 1, 0, 0, 0, 1, 0. Now the not bars occur if you're going to count in binary from 0 upward to the maximum value. The not bars come in the positions where the zeros are in this truth table down here. All right? Like I said, it's the opposite. We use the OR instead of the AND. We use a capital letter instead of the lowercase letter. And we put the not bars, where the ones go instead of where the zeros go. Okay? Again, bird's eye view. Now, let's look and see what's going on at a lower level. Okay, so just like before, I can say F equals M0, M1, M2. The capital M means I'm using max terms. And when I use max terms, I AND these guys together, right? Okay, these are ORed internally and then ANDed together, I could say externally, in this expression here. Again, look up here. These guys, little m's, are all ANDed together internally, and then they're ORed together externally in this expression up here. Okay? And I'm just reversing everything, which is literally what's going on with the Morgans Theorem. You can just see it waiting in the wings to pop out at you and surprise you. Okay, so what happens here? Let's change. Let's expand these max terms, the so-called max terms, the uppercase M terms, right? So I want to say F equals M0 and M1 and M2 and M4. Okay. Just like before, let's look ahead a minute. These cases, M0, M1, M2, M4, look what's going on. M0 here, I got a 0 here. Before, I was looking at all the cases when there was going to be a 1 over here. Now I'm going to look at all the cases when there's a 0, right? M0 is a 0 here. M1 is going to be a 0 over here. M2 is going to be a 0 over here. M4 is going to be in a 0 here. And in all other cases, we have a 1. All right, so leaping ahead, continuing the theme that's going on in here, where this guy was all the so-called min terms. M1, M2, M4, M7. M1 was a 1, M2 was a 1, and so on. Again, just flipped around the other way. Okay, so I beat that dead horse enough. All right, so what do we do here? Well, we say instead of the ands, rather ORing together all these expressions that were filled with ands, I'm going to AND together now all these expressions that are filled with ORs. Okay? And just like the table above, look what's going on here. In this case, there's a single row where there's a 0 and all other rows have 1s. Okay, where the other one up here had a single row where you had a 1 and all other cases were 0s. All right, again, the opposite of what we had above. It's a mirror image. Okay, what is this going to do here? In the case when I say A or B or C, remember the truth table for the OR gate at the top of this document, right? So we go back to the top and we come down to the OR gate. The OR was always a 1 except the one and only one case when all the inputs are 0s. Again, mirror image, right? What was the AND? The and is always a 0, except in the one and only one case when all the inputs are a 1. No matter how many inputs there are, there will be one single row when the AND gate will express a 1, and all other cases will be 0. And no matter how many inputs there are with an OR gate, there'll be one and only only one row where the output will be 0, and all the other rows will be a 1. This is great fodder for quizzes, okay? Warning, okay. So let's come back up here and look at what we're going to be looking at here. Okay, so we were looking at the uppercase m's. All right, so what's going on here? So in this table here, again, we're looking at an OR function. So clearly, we're going to have all ones and then a single 0 in here. Clearly, there's going to be all ones here and a single 0, all ones and a single 0, all ones and a single 0 in each one of these cases. Why? Because all the inputs are accounted for with either the true, without a bar, or the false or negated or barred form of the input. All right, so this guy is going to be false if and only if A is false, B is false, and C is false. And that's the guy here. That's your M0. This guy here will be false if and only if A is a 0, and when B is a 0, and when C bar is a 0. So that's when A is 0, B is 0, and C is a 1, because C bar becomes a 0. That's the one and only one time. This thing will be a 0. The one and only one time for this guy here to be a 0 is when this guy here is a 1 and A and C are 0s, right? Again, A bar, B, C, all right? A bar is a 0 and B is a 0 and C is a 0. Then and only then do I have a case where this is a 0. Now, because I AND all of these together, right, and you can see it hiding in here as well. Well, obviously, if all of those terms are a 1, then only then is the F equal to 1. Here, they're all a 1 here. It's 1. All of them are 1s here. It's a 1. Uh-oh, I got a 0 here. Well, this and that and that and that is not true, so I got a 0. All of them are 1s here, so I got a 1. All of them are not 1 here, so I got a 0, and so on for these other two lines, right? Okay, so what's going on here? The mechanics and the product of sums is based on identifying those specific function input patterns where the output is false, exactly opposite of the sum of products. Then by using an AND function, I will set the output to be false, and any time any one of those input terms is false, right? As long as M0, M1, M2, and M4 are all true, then F is true. And most of the time, well, half the time in this example, that is correct. It is true. When this term here does not recognize something and force the output to become a 0 by contributing a false to this expression up here, all right, then the output has to be a false. Okay? So what we're doing with these terms here, with these expressions, I should say, these define those cases when I know F needs to be a 0. Okay? Up here, each of these defines the one and only one case, one row in the table, when I know the output function F needs to be a 1. That's all there is to it. Okay? Again, you don't need to memorize all this junk because you should already know how to count in binary. Okay? We'll talk more about counting in binary if you're having trouble with that in a minute. Well, a future video. I won't do it in this video. Okay. So what is the relationship between these two? Well, this whole mirror image thing should, and me going on and on about the Morgans Theorem should show, should suggest, spoiler alert, hiding in here is De Morgan's theorem. So it turns out that M5 with a bar over it is the same thing as little m, I should say big M5. The max term negating the max term, complementing the max term, is the same as the min term. And that's true because of De Morgan's theorem. Well, here's how we show this. Well, what is big M5? Well, as defined, it's this. Okay, go up and look at it if you can't remember. Okay, right? 5 is 1, 0, 1 in binary, and you can see that the bars coincide with those ones. Little m5. Again, 1, 0, 1 in binary, and because it's the min term, the bar coincides with the 0 this time. So 1, 0, 1, it's going to look like that. All right. Again, you can go up and look at in the chart if you want, or you can use the technique I described. Okay. Now, anytime I want, I can just complement both sides, right? If, x equals y, then x bar equals y bar, right? That's just like multiplying two sides of an algebraic equation by -1 or something like that. All right, you can do the same thing on both sides. Okay. And I do this on purpose so that I can apply De Morgan's theorem number 1 that's defined above. Let's go ahead and have a quick review and see what it looks like in case we forgot. De Morgan's 1. In both cases, all right, here's how I actually think about De Morgan's theorem. When you have this situation here, a NOR function or a NAND function, anytime I want, I can break this bar into two pieces if I flip this over. Look what's going on. If I break it in two, I get an A bar and I get a B bar. Well, there's my A bar and there's my B bar right here. Okay. And if I flip this over, the OR becomes AND. I don't even care which way I'm going. You can do it both ways. If I got a NAND down here, I break the bar in two, break the bar, and flip this thing over. Well, if I flip that over, I get this. And if I break the one bar into two bars, I get this guy over here. That's all you got to do for remembering De Morgan's. Break the bar, flip this thing over. Okay? Now, you can also do it the other way. I can join the bar and flip it over as well, right? You think about that, right? You got A bar ANDed with a B bar. If I connect this bar and that one together and flip this over, I get this. Same down here. If I got an A bar ORed with a B bar, connect the bar together, flip that over, and I get this. All right? Done. You don't have to get into all the nitty-gritty details. Break the bar, flip it over. Or connect the bar and flip it over. That's, to me, easier to remember. You can do whatever you want. That's how I do it. Okay. Given these two things, I want to prove that M5, big M5 bar, max term M5, inverted equals this guy down here, the min term. All right, so if I put bars on both sides, I do this on purpose so that I can break it and flip these thingies over by applying De Morgan's theorem. Right? That's why I put the bars in there. So I got A bar with another bar on top. So that's just A bar bar. Okay, I flip this one over. I have B. I broke the bar, so the bar falls down on top of the B. I got a B bar, and I flip this guy over here, and I got a C bar with an extra bar, and I end up with a C bar bar. Okay, by the way, De Morgan's theorem applies to things with more than two inputs as well. Okay? All right, so don't think I'm cheating here. In general terms, it can apply to as many inputs as you want, but they all have to have the same thing in here. I can't say A, or B and C. No. All these have to be the same operator with a bar on there. So I can break it into 3 or break it into 20 or however many there are. Okay, provided that they're all the same when they flip over. Okay. All righty. So I get to here. I can then apply the double negation law to A. Not A is the same thing as A, and B bar is not is as it is. C double bar is the same as C. Well, by definition, this is M5. Okay, therefore M5 bar does in fact equal little M5. Okay, thanks to our friend De Morgan, who we proved above, is certainly for 2 inputs with an exhaustive truth table. You can prove it for 3 with an exhaustive truth table just as easily, all right? Well, it's twice as much work because there's twice as much rows, but the same logic, right? Okay, no pun intended. All righty, and the same thing happens when you want to convert from a midterm to a max term, right? So prove that M5 bar equals little m5. Well, we can also ask to be proved that little m5 bar is the same thing as big M5 by using the other of the 2 De Morgan's laws, which both are applied in the exact same way. And I use the exact same technique by adding a bar on both sides, break the bar, flip the operator upside down, and then remove my double negatives, and then stand back and observe that, hey, look at this. That thing there is the exact same as this one here. Therefore, little m5 bar equals big M5. Again, this whole mirror image thing and De Morgan's coming into play. Wonderful. You can work in either one anytime you want. So that begs the question, if they're really the same thing, who cares? Why do we even look at both kinds? Well, it turns out that in any given situation, the one I gave you before up here, we expressed two examples wherein I had 4 cases where there were zeros here and 4 cases where there were ones up here out of the total of 8 possible cases, right? In both cases. It's a 50-50 bet. However, if you have a situation where I have 1, 2, 3, 4, 5 cases when I have all the output set to 0, and I only have 3 cases when the output is a 1, choose the one with lesser terms in it because you have less work to do. It's as simple as that. I only got 3 ones in this example. Use this one. There's only 3 terms. Oh no, I want to make it hard for myself and work with all this mess down here. That's why we want to know that we can use either one. And if we really want to, we can convert back and forth. It's the mirror image. It doesn't matter which one you use. Choose the one with less work. Be the internal lazy programmer that you strive to be in life. All right, don't make things harder for yourself than need to be. That's what this is all about. All right, now bringing it on home. Now that we've complicated our lives to death with these massive equations, on the other hand, we've made it easier, right? I don't know what this function is, but I can clearly define the min term that describes this, the min term that describes that, min term that describes that. It is this. It's brain dead. I don't have to think about it because you get the A bar, B, C. Clearly, that's your A bar and your B and C right there. You got your A, B bar, C. That's this one right here. Your A, your B bar, and your C. Remember, in the min terms, the bars coincide with the zeros. And the lack of bars, A, B, C, coincide with the ones. All right, don't have to think much about it. I just got to remember whether the little m has the bars over the zeros, and the big M over here has the bars over the ones. Right. Other than that, it's straightforward and simple. Okay. Except for I have these giant equations. I need to be able to simplify those. I need to be able to factor these down to a minimum expression. So one last application of the Boolean laws. Let's walk through this. Let's take this case here. I got a situation where I've got 1, 2, 3, 4, 5 min terms if I use the sum of products, or 1, 2, 3 cases if I use the max terms and go with the product of sums. All right. If I wanted to express this and come up with the simplest, most reduced expression, I'm going to use product of sums. But for the sake of discussion, we're going to do both. Here's the sum of products and all the laws on how to reduce it down, and here's product of sums. Clearly, you can see. Let me shrink this down a little bit so we can get both on the screen at once. Clearly, we can see there's less work going on, or rather, I'm sorry, there's more work going on up here than there is down here. Spoiler alert, in both cases, we end up with A or B and C bar as the most reduced form after we jumble around and apply the Boolean algebra laws, okay? So let's look at one last walkthrough of applying the laws to reduce these things. Let's see what's going on. If I say, look, here's the case with min terms, right? There were 5 of those. 1, 2, 3, 4, 5. There better be 5 of these that go along with the 5 ones up there, okay? Given this, I'm going to expand the terms using the ones and zeros with the bars and not the bars. And if I can't do that, I can look it up on the table above. And then I can start thinking about the laws and how to apply them. Well, look what's going on in here. What do we know? Well, I got a A and a B and a C bar. And here's got an A and a B and a C. I can apply the distributive property to factor out the common part here and here of these two guys over there. And I can get A ANDed with B ANDed with the C bar or C. Okay? This is a little tricky, the distributive property. I'm treating A ANDed with B as a single value. Call that X, right? X ANDed with C bar or X, again, ANDed with C. And maybe you can see how the distributive property applies more intuitively. This X, again, appears over here. X ANDed with this guy, right? Well, that happens to be able to apply to both of these, right? I got A ANDed with B bar, both occurring in here as well, okay? So both this guy here and this guy over there, both I applied the distributive property of AND over OR as defined in the laws above. Okay. Complementation of OR. Well, what do I got? Well, if I got C bar ORed with C, clearly that's always going to be a 1, and it actually always a 1 over here. Okay, and then I can use the identity property for AND, call this whole thing X ANDed with 1. Well, that's the same thing as just X, is it not? So you throw away the 1. You got A ANDed with B here, and this same thing happens over there, and you ended up with A ANDed with B bar in that case, and we're just copying this term down here for now. We're not even paying attention. We're just playing around with the stuff on the right here, okay? Now, once again, we got the distributive property. Why? Because we can factor the A out here. A ANDed with both B bar or B. That's the distributive property working in action. A ANDed with this guy, right? Well, now I got B bar ORed with B again, which is again 1, and I get the complementation and the identity. So now all this over here, who cares? All this junk boils down to, well, look, if A is true, then F must be true. So we've applied all these laws, and we've made the observation, look, in all cases when A is true, F is true. Well, you do this a lot. I wouldn't even bother wasting my time even expressing all these terms. I would have just written down A. I would have started right here. Why? Because I've done this enough, and I know. You can do some of these reductions in your head. In all cases when A is true, F is true, I would have warped right to here. Okay, and look what we got. We got when A is true, F must be true. Or the one and only one case when A is false and B is true and C is false. Well, that describes this row right here. That's my M2. Okay, that was just this guy here, and you see me propagating that down. All right, now there's another thing we can, a spoiler alert going on here. Look, this thing here is also going to reduce down. Obviously, there's more work going on here, right? Let's look at this for a second. If we have B high and C low, that's another way of talking about this. You'll hear people calling ones highs and zeros lows. And I'll mix terminology depending on what I'm thinking about while I'm talking about these things. Usually when I'm talking about schematics and electronics and gates, we refer to highs and lows. In truth tables, ones and zeros are trues and false, all right? Sorry about mixing the terms. When B is high and C is low, and I just did it again, when B is true and C is false, there only happens in 2 cases in this truth table. There are no other situations when B is a 1 and C is a 0. Just these 2. And look what happens. F is true in both of those cases. So, spoiler alert, this whole A is going to ultimately go away. I'm just looking ahead here, all right? So, once again, we're starting right here. We have 2 situations. 1, when A is true, F is true in all cases. Or, the one other time, in addition to that, it describes this row here, okay? So where are we going? Well, we're going to see that the A on the left, what's going to happen is this is going to ultimately go away, all right? Okay, so what do we got going on here? I can reverse the order in what's going on by just use the commutative property. I want to move that thing over to the left, okay? Why I did that, I don't know. The it's so that these match exactly the order in which I wrote the Boolean laws above, okay? Commutative property does this. The associative property of OR, it doesn't matter, or rather the AND, I'm sorry. The associativity of AND says it doesn't matter which order I do these in. A and B and C, or I can do the B and the C or whatever. I'm going to just throw in some parentheses here because I can. That's what the associative property allows me to do. Now that I've done this, it makes it a little bit easier for me to see what's going on and how to apply a distributive property, because I can now say A or A bar here, okay, factor that out. or I can do the rather and, which is this operator here. That's where that goes. Again, this works just like adding and multiplying and so on, and factoring and reverse factoring in regular old algebra like we learned in school. I can take the A ORed with then this guy over here, the B and the C bar. All right, now I did this on purpose because I could see where this thing here was going. Right, I wanted to get this out of there. A ORed A bar. Well, that's always a 1. And we've seen before, we can apply then the complementation law to declare that that is always true. And then we can say that that's the identity property for and throw all this away and leave us with this. Like I said, we get rid of this A bar in this case, quite literally, leaving us with the B and the C bar. That's kind of where we ended up down. That's exactly where we ended up down there. So when A is true, or B is a 1 and C is a 0, in any situation where that is true, then F is a 1. And that's exactly what we got. When A is a 1, F is a 1. Or if B is a 1 and C is a 0, F is a 1. And it's redundant, but also true here when B is a 1 and C is a 0. And it's these redundant cases, just like this. There's 4 redundant cases where we don't care what the values of B and C are. We always know F is 1. We only have to look at A. If A is a 1, I know F is going to be a 1. Okay? If A is a 0, well, we got a little more work to do. We got to say, well, we need to know that in this one other case, F could also be 1, all right? So that reduces down to this thing here. Now, to do the same thing with product of sums, again, we can apply all the laws and we can expand our terms, apply all the laws. What's going on here? It's going to look basically the same. There's not that many laws. Distributive property. What do we got going on over here? We're going to factor out, what do we got? C or C bar. We're playing around with this guy over here. Yeah, we've got an A or B that occurs in both of these terms. So we can factor out the A or B. And then we can AND that with the C, the OR with the C bar. And again, we end up with the complementation, makes that into always being a 1. And because it's ANDed with the other things, we throw it away, do the identity law. Now we have a, what are we going down? The distributive property. We can factor this A out. All right, it appears in both of these expressions here. So I can factor the A out, and I end up with A ORed with the B and the B bar or C. That comes down again, just like multiplication, division, or multiplication and addition in high school algebra or junior high or whenever we learn that. I can't remember. So we end up with this guy down here, right? We can also then apply the distributive property again because we see, what do we got going on here? We have, oh, we can run, we're going to run the distributive property in reverse, okay? What we're going to do is we're going to take the B ANDed with the B bar, and then we're going to take that and OR it with the B ANDed with C bar, okay? So we're not using the distributive property to take a big thingy and make it small. We're taking it to make it a little one to make it big, right? So, and I did this on purpose because I could see this going on in here. And once you got a B ANDed with B bar, we know that's always false, okay? It's always 0. Complementation law tells us that, right? And then we can use the identity law and throw that away because 0 ORed with anything, you just throw this away and leaves us with A or B ANDed with C bar. This is the exact same thing as this. We ended up in the same place. Okay, therefore, you want to take the shorter road. Okay, there's less work to do. That's the takeaway. When you want to choose one over the other, if you're free to do so. All right. Again, look at these tables. Look at when you have the bars, when you don't have the bars. Notice that the patterns match the 1s and 0s. I cannot stress that enough. All right, with this in mind, you have been fully equipped to apply the laws of Boolean algebra to make any machine you'd ever want that executes code expressed in imperative programming languages. So that'll be welcome to the rest of the tutorial, the rest of the class. Okay. Thanks a lot for watching. I'll see you next time. Bye-bye.